Okay. So we were considering the homogeneous and non-homogeneous problems. So given AX equals to B, okay, which is usually said to be a non-homogeneous problem, if B is identically zero, then the problem is said to be homogeneous. Okay. And as I said, we say the problem is consistent if there is a solution. So for a non-homogeneous problem, there are three possibilities, right? So you may have only one solution or many solutions. And in those two cases, we say the system is consistent. Or the problem may not have any solution, which is inconsistent case. But in case of homogeneous problem, it is always the consistent, right? Because x is zero is mapped to zero. In so anyway, given this, ax equals to zero is if is given, then let k be a set of the solutions for the ax equals to zero. Then this k, the solutions, will be just the space, the null space for L sub a operator, so that the K will be a subspace of Fn of dimension n minus rank. And here rank may be obtained from the matrix or the left multiplication operator. So if given m by m matrix, if m, the number of equations, is less than the number of variables, unknowns, n, then ax equals 0 must have a non-zero solution. Okay, right? So in other words, so in other words, if m is strictly less than n, then then L sub a is not one to one, right? It is not one. It cannot be one to one because ax equals 0 has a non-zero solution. Then that means from Ln, I'm sorry, from Fn, Fm, this 0 is mapped from 0 and there is some non-zero solution x. So these two are mapped to 0 by L sub a. So the mapping cannot be one to one. So let us consider the examples. So if I consider these two equations in three unknowns, then the rank cannot be 3, right? So maximum possible rank of this matrix A will be 2. And in fact, these two, so the rank of matrix A is 2. So dimension of K will be 1. So there will be some non-zero solutions. And as I said, L sub A is not one to one in this case. So for instance, this vector is a solution of the previous problem. This will be a basis for K. And I know that K is one-dimensional. So I just need one non-zero vector as a basis. if I consider this a single equation in three unknowns, that means I have only one equation, three unknowns, so the rank of the coefficient matrix will be 1. So K in this case will be a two-dimensional space. So to form a basis of this K, I need two linearly independent vectors. So we need to find, we need to know how to find these two vectors, right? So please wait. I mean, I will explain today how to find these vectors when this problem is considered. Okay. So, but at this point, let me assume that somehow I found two linearly independent vectors in K. Then, since the dimension of K is 2, any vector in K will be written as a linear combination of those two vectors. But how to find these two vectors? Please wait. Now, given ax equals to b problem, if I sometimes consider ax equals to 0, then this ax equals 0 will be called the homogeneous system corresponding to ax equals to b. Then why do I consider this? Why do I consider this? Because of this following theorem 3.9. So here let K be the solution of excuse me of ax equals to b problem, the original solution set. Now let me use K sub h to denote the solution of the corresponding homogeneous problem. In other words, K sub h, so here K is the set of solutions for ax equals to b problem, and K sub h denotes the solutions for ax equals to 0 problem. Then theorem 3.9 says these two are related by this relation where S is just one solution for ax equals to b problem. Or geometrically, given K sub h, if I translate by S, you get K. Okay, but I don't want to bother you with this geometry. So the point is, given K, and I can find K sub h, or in more importantly, in many cases, people usually find K sub h. Okay, once I have K sub h, if you add just one solution to each vector in K sub h, you get the whole solution K. That is the beauty of this theorem. So then, why is it true? So let me prove this too. Okay, let me prove this theorem. So let me show that the left hand side is included in the contained in the right hand side, and the right hand side is contained in the left hand side. Okay, so let me just choose any solution S for ax equals to b problem. Okay, now if I choose any vector from K, so let me choose any vector from the left hand side. Then since K is the collection of the solutions for the non-homogeneous problem, this W will satisfy this equation. And S is one particular solution of ax equals to b. So S also satisfies this equation. So A times W minus S will be AW minus AS, and AW and AS are both B vectors, so their difference is 0. So that means this W minus S is one of the solutions for homogeneous problem because when A is multiplied to W minus S, you get 0. So W minus S is contained in K sub H. Okay, so that means it is some, so there exists a certain K which will be just the W minus S. That means W will be S plus K. So it is included in this set. Meaning, meaning if I choose any vector from K, then that vector is contained in this right hand side. So that means K is a subset of the set on the right. Now let me choose any arbitrary vector from the right hand side. So now my W is selected arbitrarily from the right hand side. That means W will be W can be written in this form where K is certain vector in K sub H. So K in K sub H, that means A times K will be 0. Okay, then when I multiply A with W, since the W is S plus K, you get A times S plus A times K. Now A times S will be B because that's how we selected S, and A times K will be 0. So B plus 0 is B. So that means when I multiply A with W, you get B. So W is one of the solutions for AX equals to B problem, meaning W is one of the elements in K. So if I choose any arbitrary vector from the left hand side, from the right hand side, that is one element in the left hand side. That means the set on the right is a subset of K. So if I combine this with this, then these two sets will be the same. So, so what is the meaning of this? So what is the meaning of this? If you, so one usage is this. From now on, I will find K sub H first, okay? And then I will add one particular solution to each solution in K sub H. Then you obtain the general solution set for AX equals to B problem. Okay, so here is the idea. From now on, somehow, okay, I will introduce this somehow part today. So I will find this K sub H. Okay, this the general set. Okay, so let me explain this way. So to find K, which is the solution set for AX equals to B. Step 1, we will find K sub H. In other words, we will solve the corresponding homogeneous problem, AX equals to 0 problem. Step 2, find just one solution S for S2 AX equals to B problem. Okay. Step 3, construct this one. That means, in other words, add this one particular solution to each vector in K sub H. Then you will find all the solutions to AX equals to B problem. Let us consider the following. So to find this, previously we found one particular solution. Oh, sorry. We considered the homogeneous problem in the example 2a moments ago. Okay. And I will show how to find this one particular solution of the non-homogeneous problem. Then the solution set can be written by this form. So what is this? Note that case of H, the homogeneous problem was the solutions to the homogeneous problem was constructed by this moments ago. So for each vector in case of H, if I add this S, then you get K, the all solutions. And S is not unique. You can add any solution. Any solutions to AX equals to B can be your S. And if you add any S, you get the whole solution. Previously, moments ago in the beginning of today's class, we considered the homogeneous problem for this system. And for that problem, the dimension of the solution space was 2, and I claimed that these two will generate that case of H. Okay. And if I add one particular solution to this problem, then you get K. Now, before I introduce how to find these solutions, the solutions to the homogeneous problem or solutions to the non-homogeneous problem, okay, before I consider this, let us consider this theorem 3.10 that will be a basis for what we are going to do. Okay, so here, let us consider this AX equals to B problem. Suppose that there are M, okay, and suppose that, oh, I'm sorry, this is not the one I mentioned. Okay, before the one okay, yeah. The main theorem I'm going to need is not this one. Sorry about that, but this is also important. So let AX equals to B be a system of n equations in n unknowns so that your A is a square. Sorry. This A is a square n by n matrix. Now, if A is invertible, then the system has exactly one solution exactly one solution for any B. And conversely, if the system has exactly one solution, then this A will be invertible. Okay? So let us prove this. Suppose that the A is invertible. Then that means A is invertible. That means A inverse exists. Then this A inverse times B vector exists. For this vector, if I multiply A, you get A inverse times B, and you get identity times B, so that you get B vector. So if I plug in A inverse B to the problem, then this system, the equation is satisfied. So A inverse B will be one of the solutions, right? So these two lines show the existence of the solution. Solution exists, right? Now, if if S is any solution to this problem, so that A times S is B, then in that case, given AS equals to B, if I pre-multiply the inverse of A, okay, you still get the identity. Now, from the left hand side, you get S. From the right hand side, you get A inverse B. What does that mean? If S is any solution, then S must be identical to the A inverse B solution. That means the solution will be unique. So for any B, we can find the solution, and the solution will be A inverse times B. That's the only solution you have. Now, suppose that the system has exactly one solution, S. And case of H, let case of H denote the solutions to the homogeneous problem. Then by the previous theorem, the K is the set of S plus K sub H. Now since the problem I assume that this problem has only one solution S, so this line implies that K consists of only S. Then K, which consists of only one S, will be the same as this. That implies that K sub H will be the set of zero vector. In other words, the zero is the only solution. So that means zero is the only solution to AX equals to zero homogeneous problem. Okay. Then we learned that A is invertible. So, so any n by m matrix will be invertible if and only if AX equals to B has exactly one solution for any B. So that was the claim in theorem 310. And that means my L sub A must be 1 to 1 and on to, so that it is invertible. So in that case, your A will be invertible. So I just derived some three statements which are equivalent. In example 4, so if consider the following system of three equations in three unknowns, and when I consider the coefficient matrix, previously we found its inverse. So A inverse exists. So if the inverse exists, then when I multiply the inverse of A to the right hand side of vector, we get the solution. And this solution will be the only solution we have for the given problem. Now, theorem 3.11 is quite interesting. So here, let's consider AX equals to B problem. So here A can be any m by n. So there is no restriction regarding the size of A. So A is any m by m matrix, and let me consider AX equals to B problem. Then the system is consistent, meaning the system has a solution if and only if rank of A equals rank of the rank of the coefficient matrix equals the rank of the augmented matrix. So here A is the coefficient matrix and the A bar B is the augmented matrix. If these two matrices have the same rank, then the problem will have a solution, and vice versa. If the problem has a solution, then rank of A is not increased by adding the right hand side vector, right? Now, how can I prove this? So, so if AX equals to B has a solution, then that means since AX is just representing a linear combination of the columns in A matrix, AX equals to B has a solution is equivalent to saying B is in the range of L sub A, right? And because A times X represents is a linear combination of columns in A matrix. Now, the range of L sub A thus is the collection of all the linear combinations in A matrix. And that collection was called the span of these columns, right? So span of the columns of A, that is the collection of all the linear combinations of the columns in A matrix. So if you can construct B using the columns in A matrix, then AX equals to B will have a solution. And please remember, okay, that means that means the solution X will be the weights used in the linear combination to construct a B vector. Anyway, so B is included in the span of these columns in A. If okay, that means when I consider the span of the columns in A and the span of the columns in A plus B vector, so please note that I just added B here. If B is included in the span of the columns in A, the adding this B vector does not change the space generated by these columns, right? And that means the span of these will generate one space, and that space will be the same as the space generated by the n columns in A and B vector. So if these two spaces are the same, then their dimensions will be the same, and the dimension of those spaces is another name for this dimension is the rank. So rank of A will be the same as rank of this augmented matrix. So what does that mean? So, so the conclusion here is this. So the system AX equals to B is consistent, or in other words, it has a solution if and only if rank of A and the coefficient matrix and the rank of the augmented matrix will be the same, so that so that so that B is included in the span of the columns in A matrix. So the highlighted statements are all equivalent, right? So that means this rightmost column B is that B is a linear combination of the columns in A matrix. So so that means B is a linear combination, as I said above, the columns in A. And as I said, solution X will denote the weights used in this linear combination, right? So this is one of the equivalent to, so let me say. So the previous theorem says AX equals to B is consistent, or in other words, has a solution. So that is equivalent to saying that B is in the range of this mapping, which means B is a linear combination of the columns in A matrix, because this range of L sub A is the span of the columns in A matrix. So if B belongs to the span, then that means that B is one of the vectors in this space, meaning B is a linear combination of the columns in A. And in that case, the rank of the coefficient matrix and rank of this augmented matrix will be the same. Okay? In other words, B, the addition of B to the matrix does not increase the rank. Okay? The addition of B does not increase the rank. So those are equivalent statements, and I will add a few more statements for this property. In example 5, if I consider this matrix, then coefficient matrix A is this 2 by 2 matrix, and the augmented matrix is this 2 by 3, right? The rank of A is 1, while rank of the augmented matrix is 2, so their ranks are different. Then that means there is no solution because the system is not consistent. In example 6, okay, Let us consider this mapping T, which maps this triple A1, A2, A3 to this triple. And given this mapping, I want to determine whether 332 is in the range of this mapping. If this vector is in the range, then when I consider this problem, when I plug in, when this problem is considered, the problem must be consistent. Okay? And if that is consistent, then the rank of the coefficient matrix must be the same as the rank of the augmented matrix. And you can check, but the rank of the coefficient matrix is 2, and the rank of the augmented matrix is 3 in this example. You can easily check this. So since these two ranks are different, then that means the system is inconsistent. If that is inconsistent, then that means 332 vector is not in the range of this mapping. Now, these are some problems in the exercise, and I hope, okay, you spend some time to think about these three situations. So first problem is this: if A is on m by n and B is n by p, then A times B, this product can be written as a sum of n matrices of rank at most 1. Okay, so A times B will give you some matrix, right? And I want to, so here, if A is m by m times n, m by n, and if B is n by p, then A times B will be m by p matrix, right? And I want to write down this by the sum of n m by p matrix, okay? And each m by p matrix in this summation has rank 0 or 1. So I want to write down AB as a sum of these and such matrices. Okay? So please think about this. I mean, and please think about the way to construct this M by P matrix used in the summation. And number two, if A is an M by M matrix with rank M, then is M less than N? Is M less than N, or is M greater than N? What is the shape of this matrix? Is it this shape or this shape? Which one is true? If the rank is M, the number of rows, then the second one cannot be the situation, right? M will be less than or equal to N. That's what I can derive from the first statement. And if B is an n by p matrix with rank n, then by the same reasoning, n, your B n will be less than or equal to p, right? So here m is less than or equal to n, and n is less than or equal to p. In that situation, determine the rank of A times B and justify your answer. This is quite an interesting question. Okay. And number three, prove or give a counterexample to the following statement. If the coefficient matrix of a system of m equations in n unknowns has rank m, then the system has a solution. If you believe this is true, you should be able to prove it. If you believe it is false, then you should be able to find a counterexample. So I like some questions like some statements like this. Okay. And because these are quite useful and important statements, which has many applications in the later chapters. Some of them will be considered in our semester, some will be used in the fourth semester. So, so these three statements are quite useful in applications. So please think about these. So that's what we considered in section 3. And in section 4, we will consider the computational aspects, meaning if I give you the systems of linear equations, you should be able to find the solutions to the corresponding homogeneous problems, and you should be able to find the solutions for non-homogeneous problems. Okay, so we will consider some techniques in this section. Now, first, we say two linear systems, okay, are said to be equivalent if they have the same solution set. Then we say two systems are equivalent. Now, our our goal will be the following. Given some ax equals to b problem, we will derive some systems which are simpler to handle but equivalent. Okay? So I will introduce simpler and simpler but equivalent systems, and then using somewhat very simple problem to find the solution. And since that problem is consistent, I mean equivalent to the original problem, that will give you the solution to the original problem. I mean, let me explain with the theorems and examples. Okay. So theorem 13, theorem 13 is the following. Suppose that I have ax equals to b problem. Now, ax, so if this is a, yeah, this is a system of m equations in n unknowns. So your A is on m by n matrix, and X is a vector with n columns, n entries, equals to B vector with m entries. Now, given this problem, the theorem 13 says if I pre-multiply some m by m invertible matrix, so if C denotes an invertible m by m matrix, if I multiply the C, the system, this is equivalent to ax equals to b. That means, okay, first of all, let us prove this statement, and then let us consider its meaning. So suppose that K denotes the solution set for the original problem ax equals to b, and K prime denotes the solution set for the second problem cax equals to cb. Now, if I choose any vector from the original problem, then that w will satisfy the given equation. Then when I pre-multiply c to this equation, we still have this relation, so that means w is a solution in K prime. So that means when I choose an arbitrary vector from K that is that is included in K prime, so meaning K is a subset of K prime. Now, if I choose any vector from K prime, then this W will satisfy this new equation. Now, now, now this A times W, this A is obtained by multiplying the identity matrix to A, and since matrix multiplication is associative, we can consider, right, this is, we can, A can be written as identity times A, which is the same as C inverse times C times A times W. Now C times A times W is the same as C times B, and since matrix multiplication is associative, I can perform C inverse times C again, which is the identity, so you get B vector. So that means W will satisfy the original problem, meaning K prime is included. That is a subset of K. So by combining these two facts, we can derive this one. So what is the point of this theorem? So, so if you multiply any invertible matrix to the right, the coefficient matrix and the right hand side of the vector, it does not alter the solution set, right? So that is the meaning of this theorem 3.13. So multiplication by any invertible matrix, invertible matrix, it does not change the solution set. As a special case, one of the invertible matrices is an elementary matrix, right? So if I pre-multiply any elementary matrix, it does not change the solution set. Now, what does that mean? So this corollary says, so any invertible matrix, say an elementary matrix, does not change the solution set. Now, multiplication by an elementary matrix is the same as performing any elementary row operation, right? So multiplication by an elementary matrix from the left that is equivalent to performing an elementary row operation, right? If you multiply an elementary matrix from the right, that is equivalent to elementary column operation, right? But if you multiply any elementary matrix from the left, which was in the case in the theorem, that is equivalent to performing an elementary row operation to the system of equations, right? So, so the previous theorem is can be said as the following. Given some system of equations, AX equals the B problem, if you perform any elementary row operation to change the coefficient and the right hand side of vector, the resulting system will have the same solution set as the original problem. Okay, so that is the result This is the trick we are going to use, okay, in this section. So given system of equations, from now on, I will construct the augmented matrix, and then I will perform row operations. Okay? Because, and then I can find the corresponding system of equations. And these systems will have the same solutions. The solution set is shared by all the corresponding the systems. Okay, that's how we are going to solve the problem. So consider the following example. Suppose that I want to consider this problem, whose augmented matrix is this. Okay. Now, given this problem, given this augmented matrix, let me exchange first row with the third row to get 1 in the first row. Okay, I mean to get 1 in the first row, first column. Okay, so in the leftmost non-zero column, you create 1 in the first row. Okay, if needed, you can interchange some rows, or you can perform some scaling. So I have 1 in the leftmost non-zero column, which is the first column in this case. Okay. Now, so I have this 1 here. Okay. Using this 1, I want to change these 1 and 3, the numbers below that 1, to 0. Now, when I change these 1 and 3 to zeros, I will use only type 3 row operation. In other words, replacement. Meaning row 2 will be replaced by row 2 plus some number multiple of row 1. And in a similar way, row 3 will be replaced by existing row 3 plus some number multiple of row 1. Okay. So in order to change this 1 in the second row, first column, which number shall I multiply to the first row and then add it to the second row? Negative 1. So if I multiply negative 1 to the first row and then add it to the second row, this 1 in the first row, the second row, first column, will become 0. And so this negative 1 is the ratio, the 1, sorry, the number to be erased, to be changed to 0, divided by the 1, okay, in the first row, first column, okay, with minus sign. Okay, so in this case, so negative 1 is the number to be changed to 0 with minus sign. So that you multiply that number to the first row and then add it to the second row, then 1 in the second row first column will become 0. And you multiply, in order to change this 3 to 0, you multiply negative 3 to the first row and then add it to the third row, then 3 will become 0. And when you perform these two row operations, the entries in the second and third rows will be changed accordingly, right? So I found 1 in the leftmost non-zero column, and then I changed the numbers below that number to zeros. Okay, so by means of type 3 row operations, and use the first row to obtain zeros in the remaining positions of the leftmost non-zero column, meaning these two numbers are now 0. Okay? Then, what is the next step? You go to the next row in the leftmost possible column. Okay? And then you go there. So what is the leftmost possible column? That is the second column. And what is the next row? Second row. So that means you create 1 there in the second row, second column. And then using this 1, we perform the same type 3 elementary row operation to obtain zeros below this one in the second row, second column. In this example, I had negative 4 initially. Okay. Oh, but before I do that, how can I obtain negative 1 in the second row, second column from this matrix? Okay. So I want to have 1 in the second row, second column here. So what you can do is you can multiply negative 1 to the second row. Then you get this 1 in the second row, second column. Now using this 1, I want to change this negative 4 to 0. So what you can do is you can multiply 4 to the second row and then add it to the third row. Okay? And when you eliminate this negative 4, I play with the second row. Okay? I do not play with the first row. Okay? So this is what I get then. Okay? Then I repeat this step 3 and 4. So I go to the next leftmost possible column next to row. So we were considering second row, second column. The next row is the third row. And then if I go to the next column, actually if I consider the third row, third column, I have 0. And if I temporarily discard, okay, so let me explain this from the beginning one more time. So this is what we had. Okay? Now the first statement is this: in the leftmost non-zero column, create a 1 in the first row. So here I want to create, so the leftmost leftmost column, non-zero column, is the first column. That is non-zero. And in the first row, I want to have 1. but now I had three, right? So there are several ways to have one. You may interchange first row with the second row, then you will have one. You may interchange first row with third row, that is also possible. Or you may multiply one third to the first row entries. Okay, these are all possible. There is no one fixed way. You can do anything, any of these three ways, then you will have one. Then, of course, depending on your choice, the entries may be different. So if I interchange it, the first row and the third rows, then this is what you get. But this is not the only way to perform this operation. You may interchange first row with the second row instead of the third one. Anyway, once you have one in the first row in the first column, by performing the replacement operation, okay, and when you perform the replacement operation, you must use the first row to obtain zeros in the remaining positions of the leftmost non-zero column, meaning 1 and 3 below that 1 to 0. They must, this 1 and 3 in the first column must be changed to zeros. Then you go to the, then you create a 1 in the next row in the leftmost possible column, and at that point you do not use previous rows, meaning you temporarily forget the first row and you consider only the second to the last rows only. Okay, so for a moment you do not touch the previous rows. So in that case, if I temporarily hide the first row, the leftmost non-zero column is the second column, because in the first column you have only zeros. So in the second column, that is non-zero column, the next row is the second row. In the second row, you create 1. And previously I had -1, so I multiply -1 to change this -1 to 1. And then, since the first row is hidden, okay, I do not play with the first row. Using the second row, you change this -4 to 0, now, like this. And then you hide two previous, so you hide two rows, and then you consider leftmost non-zero column. In this case, first three columns are all zeros. So the next non-zero leftmost column will be the fourth column. Okay? The next row is the third row. So I want to have 1 in the third row, fourth column. How can I do that? You can multiply -1/3 to this third row. Then your third row becomes this. Okay? Then when I look at this, so this is the 1, here is the 1, here is the 1 I obtained in these steps. Okay? And below those ones, you have just the zeros, right? Such matrix will be called a upper triangular matrix. Okay, so I have ones here, and below those ones, I have only zeros. So I have zeros, 0. Okay, I don't care about the entries in the third column, but I just consider the ones within the circles. That's how I created in these steps. And below those ones, I have only zeros, right? And I don't have any further row, so I need to stop there. And this is matrix will be called an upper triangular matrix. Now, some people call these ones as pivots, okay? And the columns having these pivots are called pivot columns. So those are the columns having pivots. So in this example, first, second, and fourth columns are the pivot columns. Okay. Now, now, what does that mean? First of all, okay, before I do this, let me consider this. So this is the augmented matrix. Now, I obtained this, and that what does that mean? That means what is the corresponding system of equations? First, the four columns are the coefficients of the unknowns, while the right-hand side of the vector is the values on the right, right? So so we have x1, x2, yeah. So this matrix in this slide represents system of equations corresponding to x1 plus 2x2 plus x3 minus x4 equals to 2. And since the first number in the second row is 0, that 0 is the coefficient of x1, and x2 minus x4 is negative 1, corresponds to the second row. And the third row implies that first three numbers are zeros, and those are the coefficients of x1, x2, and x3. So x4 is the first non-zero term, equals to 3. So if I consider this system of three equations, then this system is equivalent to the given problem, because I just obtained these matrices by performing elementary row operation. And this corollary says if I perform elementary row operation to certain augmented matrix, the solution set of the corresponding system of equations is not changed. Right? So this problem is equivalent to this one. Of course, that problem is equivalent to the system of equations corresponding to this augmented matrix, like x1 plus 2x2 plus x3 minus x4 equals to 2, and x2 minus x4 equals to negative 1, minus 4x2 plus x4 equals to minus 5. Yes, of course, this system is also equivalent to the given problem. But instead of this system, we prefer this because it has this system has less unknowns in this problem, right? Especially if you look at the third equation, you have only one unknown, x4. And we could identify its value from this, right? So this is Very simple to calculate, right? Now, we can stop here if we want, but I can go a little bit further. So from step 1 to step 5, I focused on the entries, okay, the numbers below the pivots. So please note that step number 1 up to number 5 converts the numbers below the pivots to 0. And these steps, number 1 through number 5, is called forward phase. Depending on the authors and textbook, they may have different expression, but usually it is called the forward phase. Now, now I want to step 6 to the end. I want to consider now. I want to consider the entries above the pivots. So please remember these three ones are the pivots, and when I derive these three pivots, I came from the leftmost column to the right hand side. I mean, I started from the first column, then second column, then I skipped the third column, and then I came to the fourth column, and so on. So, in case of the forward phase, you go from the first column to the last column. You first consider the entries in the first column, then you consider the entries in the second column, and so on. So you go from the left to the right. Now in step 6, I want to consider it, okay, the entries above the pivots, and in that case, beginning with the last non-zero row, okay, which is the third row in this case, and add a multiples of each row to the rows above. Okay, to change these two negative ones to 0, meaning I perform the replacement operation again, type 3 operation. Okay, now which number shall I multiply to the third row to eliminate negative ones above? Just 1. If you add 1 to negative 1, you get 0. In other words, if you add third row to the second and first rows, those negative 1s above the pivot, third pivot 1, will become 0. So if you add the third row to the second and the first row, you get these two zeros. Okay, so at this point, I considered the third row first. And then you go to the next second row to eliminate the entries above the second pivot to 0. And at that point, in the case, I need to perform the replacement again. So in order to change this 2 to 0, I need to multiply negative 2 to the second row and then add it to the first row. If you do that, you get 0. And then what will be the corresponding system of equations? This. Given this, okay, please remember the pivots. What were the pivots? These three ones. Then what are the unknowns corresponding to these pivots? X1, X2, and X4. Okay, so excuse me. So these are the unknowns corresponding to the pivots, and those are called basic variables, or sometimes called they are called the pivot variables. Then we have one unknown which is not a basic variable. Okay, the remaining of variable will be called a free variable. So that is the variables, I'm sorry, which are not basic variables. Okay, so given these four unknowns, four variables, x1, x2, x3 are basic variables, and x3 is a free variable. Okay, so number 6 and number 7 converts the entries, the numbers above the pivot to 0, and those are called backward phase. Okay. Then the next step is to express the basic variables in terms of free variables. Okay. The final step is to express the basic variables in terms of free variables. Hmm? Oh, just a second. Oh, it is 11:48. Sorry about that. It is, okay. Sorry, it's too late and sorry. I didn't notice it ends. Okay, anyway, let me continue, okay, next time from this slide, okay? Thank you for listening and see you next time. Sorry about that.